In the next few lectures let us look at various types of integration schemes, and this helps us to get an idea why Gaussian quadrature is preferred for finite element calculations. So to start with, let us look at what are called Newton-Cotes rules, and under that we have the first one point rule or rectangle rule, and in rectangle rule basically for numerical integration purpose we are going to evaluate function at one point. So n is equal to 1. So basically in rectangle rule, if you have a function f(x) to evaluate integral f(x) within the limits x1 to x2, it is approximated as the function value at one of the points that is the lower bound, that is x1, function value at x1 multiplied by a weight. Here for rectangle rule weight is going to be the distance from x2 to x1, that is x2 minus x1 is going to be the weight, and function evaluated at a single point, that is x1. So by doing this basically what we are doing is whatever be the type of function, whether it is constant, linear, quadratic or any order of function, we are basically approximating that function as a constant function q0 as shown in the schematic there. So basically rectangle rule is good for evaluating integrals where f(x) is a constant. Since we are evaluating function at only one point, as you can see in the figure, the difference between the area enclosed by f(x) between points x1 x2 and the area enclosed by the curve q0 between the points x1 x2, this difference in area is going to be the error that is associated with this rectangle rule. So that is the accuracy that we are losing when we adopt rectangle rule if the function is not a constant function. But for a constant function, rectangle rule or one point rule or Newton-Cotes rules with n is equal to 1 results in accurate solution. So now let us look at 2-point rule or trapezium rule, or here the function is going to be evaluated at 2 points. So n is equal to 2. Here in the figure function f(x) is shown. So in basically in trapezium rule, to integrate f(x) between x1 and x2, what we are going to do is we are going to evaluate this function f(x) at 2 points. The 2 points are pre-decided, the 2 points are the limits between which we want to find this integral. So this f(x) is going to be evaluated at lower limit x1 and f(x) is going to be evaluated at upper limit x2. Once we have these function values, the function value at x1 is multiplied with a weight which is half the distance between x1 and x2 or x2 and x1. Similarly the function value at x2 is multiplied with a weight which is equal to half the distance between x2 and x1, that is h/2. So basically in trapezium rule we are replacing whatever function, that function we are replacing with a linear function q1 as shown in the schematic. So whatever error that is associated with this trapezium rule is the difference in area between the area enclosed by the curve between the points x1 x2 and the area enclosed by q1 between points x1 and x2. The difference between these two areas is going to be the error associated with trapezium rule, and trapezium rule is going to be accurate if function f(x) is a linear function, or trapezium rule is going to be accurate if the function order of the function is 0 or 1. Even for constant function trapezium rule is going to result in accurate solution. So this is about trapezium rule. So the formula will be exact for function of degree 1 or less. So to illustrate the procedure, let us try to evaluate this integral sin x between the limits pi over 4 and pi over 2. So lower limit is pi over 4, upper limit is pi over 2 using trapezium rule. So basically what we require is we need to find what is the distance between upper limit and lower limit. So pi over 2 minus pi over 4 is pi over 4, that is going to be h. So once we have h, we need to evaluate function, that is sin x at pi over 4 and sin x at pi over 2 multiplied with corresponding weights, which is going to be h divided by 2. In this case it is going to be pi over 4 times half, which is going to be pi over 8. All those details are given here. So h is equal to pi over 4 for this particular case. So therefore the integral is approximated in this manner, and the approximate solution turns out to be 0.6704, and this function can also be integrated exactly. So the exact solution, if we compare with exact solution, the approximate solution that we just obtained using trapezium rule, it turns out that exact solution is 0.7071. So that is the accuracy that we get using trapezium rule. So now let us go and see what is called Simpson's rule or 3-point rule, where we are going to evaluate function at 3 points. So n is equal to 3. So integral fx between the limits x1 x3, here intentionally the upper limit is named as x3. So if a function is there, if one wants to evaluate this function, integral of this function between limits x1 and x3, that is approximated using Simpson's rule in this manner: weight function at x1 multiplied by function value at x1 plus weight function at x2 multiplied by function value at x2, weight function at x3 multiplied by function value at x3. So x1, let us see where this x2 is. This x2 should be midway between x1 and x3. So once we know upper limit and lower limit, we can easily figure out what is x1 value, what is x2 value, what is x3 value. We can easily evaluate function at these points, and only thing unknowns are w1, w2, w3, and here let us see how we can evaluate this w1, w2, w3. And that procedure that we are going to follow for evaluating these weights is going to be a general procedure, which also helps us to understand how in Gauss quadrature how locations of integration points and weights are obtained. So the Simpson's rule is going to be exact for a function of degree 0, 1, 2, and this gives 3 equations in 3 unknown weighting functions w1, w2, w3. So basically if you see 3-point rule, it is going to be exact for a function of order 2. If you take trapezium rule, it is going to be exact for a function of order 1, and if you take rectangle rule, it is going to be exact for function of order 0. So what we can conclude from here is Newton-Cotes rules is that if you adopt n points, we can integrate a function of order up to n minus 1 accurately using Newton-Cotes rules. Newton-Cotes rules can either be rectangle rule or trapezium rule or Simpson's rule, or you can go for n is equal to 4 or n is equal to 5, whatever it may be. Newton-Cotes rules are going to be exact for a function with n points. Newton-Cotes rules with n points are going to be exact for a function of order n minus 1. So now let us see the procedure how to find these weights w1, w2, w3 to get to solve for 3 unknowns. We know that we require 3 equations to get a unique solution for 3 unknowns. So to evaluate this w1, w2, w3, we are going to come up with 3 equations in terms of W1, W2, W3 and solve these 3 unknowns using these 3 equations. So that is the basically the procedure to get these weights W1, W2, W3. So now let us look at the procedure. Basically in Simpson's rule a function fx is replaced or it is approximated as a quadratic function q2 as shown in the figure, and this function is evaluated at 3 points x1, x2 and x3, and x2 is midway between x1 and x3 and the distance between x1 and x2 is h, x2, x3 is h. So our job is to evaluate this function integral fx between the limits x1 and x3, and since x1 corresponds to minus h and x2 corresponds, x3 corresponds to h, if we take x2 as the origin, if you take x2 as the origin, x1 is at a distance minus h and x3 is at a distance h. So we can replace these limits x1, x3 with minus h and h. Similarly, since the function is initially is with respect to the origin that is shown with respect to the x axis, since we are defining a new axis, this function also needs to be expressed in terms of new origin, that is x2. So this fx is replaced with capital Fx. It can be easily verified that this fx, capital Fx and small fx values at any point along the curve are going to be the same. So the distance between x3 and x1 is 2h, and now the procedure goes like this. So we need to determine 3 unknowns W1, W2, W3. So let we will start with let capital Fx is equal to 1. So when capital Fx is equal to 1, integral minus h to h dx 1 dx becomes 2h, and the function value taken at any point, that is x1, x2, x3 is going to be the same, which is going to be equal to 1. So the previous approximation W1 times function evaluated at x1 plus W2 times function evaluated at x2 plus W3 times function evaluated at x3, it becomes 2h is equal to W1 plus W2 plus W3. So we got one equation. So now let us say fx is equal to x. Again apply that equation which we have already seen. So replace fx with x, integrate between the limits minus h and h, x dx and since x is a odd function and we are integrating odd function over a symmetrical domain minus h to h, the integral turns out to be 0, and this should be equal to, or this is approximated as W1 times function evaluated at x1. Here in this case x1 is nothing but minus h. So W1 times function itself is x, fx is equal to x. So function evaluated at x1 is equal to minus h, function evaluated at x2 is equal to 0, function evaluated at x3 is equal to h. So using this information we get this equation W1 times minus h plus W2 times 0 plus W3 times h. If we simplify we get equation in terms of W1 and W3, and since W2 or h function evaluated at x2 is 0. And now let us get another equation by letting f is equal to x square, and that results in the second equation that is shown, that is minus h to h x square dx. X square is a even function and we are integrating over a symmetrical domain. So we are going to get some non-zero value which turns out to be 2 over 3 h cube is equal to W1 times function evaluated at x1, and since x1 is same as minus h, that is going to be minus h square, W2 times function evaluated at x2, x2 is same as 0, so it is going to be 0 square, W3 times function evaluated at x3, function evaluated at x3 is h, function evaluated at x3 square is h square. So it becomes w3 times h square. So that is how we obtain this equation. So we got 3 equations. Since we need to determine 3 unknowns, we use this condition, let fx is equal to 1, fx is equal to x, fx is equal to x square, and using these conditions we got 3 equations. So we can solve these 3 equations for these 3 unknowns w1, w2, w3. Since we imposed while deriving these weights w1, w2, w3, we impose these conditions that the function has to be exact up to quadratic, that is x square. So Simpson's rule is going to be exact for a function of order 2, that is quadratic function. So solving these 3 equations we get w1 is equal to w3 which turns out to be h over 3, w2 turns out to be 4h over 3, and so the function or the integral fx between the limits minus h and h is approximated as 1/3 h times function evaluated at minus h, 4/3 times function evaluated at 0 plus 1/3 times function evaluated at h, sorry the first one should be at minus h, or after returning to the original function and its limits we get this equation, and where we need to keep a note that x2 is midway between x1 and x3. So basically this is the procedure that we can generalize for any number of points, Newton-Cotes rules of any number of points. To obtain the weights, this is the procedure that we can generalize. So if one wants to derive Newton-Cotes rules weights for a quartic function, that is a 4th order function, then one needs to start getting 5 equations, and so we need to start with fx is equal to 1, fx is equal to x, fx is equal to x square, fx is equal to x cube, fx is equal to x power 4. So if it is a cubic function we need to impose the condition fx is equal to 1, fx is equal to x, fx is equal to x square, fx is equal to x cube. If it is quartic function we already discussed, and if it is 5th order function we need to impose conditions fx is equal to 1 to fx is equal to x power 5. So we got 6 equations there. So we need to use 6 weights, or we need to use Newton-Cotes rules, n is equal to 6. So now let us take this example which we already solved using trapezium rule, integral sin x between the limits pi over 4 and pi over 2 using Simpson's rule. So x1 is going to be pi over 4, x2 3 is going to be pi over 2, x2 is going to be between, that is midway between pi over 4 and pi over 2. Solution h is equal to pi over 8, and function value evaluated at these 3 points and multiplied by the corresponding weights results in this, which can be simplified to this, and when we compare this solution with the exact solution which is 0.7071 we can observe that it is very closely matching with exact solution, because Simpson's rule we actually evaluated function at more number of points. So now let us look at what is the associated error with each of these 3 rules, 3 Newton-Cotes rules, that is rectangle rule, trapezium rule and Simpson's rule. So to do that let us consider a Taylor series expansion of fx, about the lower limit of integration x1. So, if we do Taylor series expansion of fx about x1, we get this equation, and integrating this equation on both sides between the limits x1 and x2 results in this, and which can be simplified to this one. And basically, if you recall, for rectangle rule, to integrate function between the limits x1 x2, what we are doing is we are evaluating function at x1 lower limit and multiplying with a weight which is equal to x2 minus x1, and we are not considering the higher order terms that are shown in the series there. So, all the higher order terms are truncated by the rectangle rule. The terms that are truncated by the rectangle rule are shown in the equation. So, rectangle rule has a dominant error term of order or of the form h square over 2 first derivative of f evaluated at x1. So, this is the error associated with rectangle rule. Similarly, we can derive or we can find what is the error associated with trapezium rule. So, consider Taylor series expansion about x1 to obtain x2. So, we get this, and multiplying by h over 2 and rearranging, we get this equation. And now what we are going to do is we are going to substitute this, that is half h square times first derivative of f evaluated x1 into the previous equation that we already looked for when we are deriving error term for rectangle rule, which is reproduced here. So, we are going to substitute the previous equation into this equation, and that results in this equation. And if you see the second equation, basically it is same as the formula that we looked for trapezium rule, except we have some higher order terms which are truncated by trapezium rule. So, trapezium rule has a dominant error term of whatever term, highest term that we did not consider in the trapezium rule, that is minus 1 over 12 h cube second derivative of function evaluated at x1. So, this is the dominant error term associated with trapezium rule. Similarly, we can derive error term, dominant error term associated with Simpson's rule. So, basically in Simpson's rule we approximated function in this manner, and where higher order terms are grouped into the form, or the dominant error term is shown as alpha times fourth derivative of function. So, now let us take where alpha is a constant coefficient, and then let us take a function, let fx be x power 4. When we substitute this, fourth derivative of x power 4 is 4 times 3 times 2, that is going to be 24. So, fourth derivative of fx is going to be 24, and alpha is there. So, 24 plus 24 alpha. So, that is the error, dominant error term associated with Simpson's rule. So, now we can also evaluate this function exactly, that is minus h to h x power 4 dx. X power 4 is an even function, and we are actually integrating it over a symmetrical domain. So, the integral value turns out to be a non-zero value, which is going to be 2 over 5 h power 5. So, we can easily back calculate what is alpha. So, the dominant error term associated with this Simpson's rule is minus 1 over 90 h power 5 fourth derivative function. So, this is how we can actually find what is the dominant error term associated with any of these Newton-Cotes rules. So, to summarize, a function between the limits or integral between the limits a to b f x dx can be approximated using this Newton-Cotes rules using this formula, where the second formula second term of this formula is associated with the dominant error term for that particular rule, and with the constants here C naught, W's and C1, all those details are given in this table. So, if one wants to select n is equal to 5, they can easily go through this table and find what is C naught and corresponding W's, and also C1 gives you idea about the dominant error term. So, this is about Newton-Cotes rules, that is rectangle rule, trapezium rule, Simpson's rule. Sometimes we may not evaluate an integral at a single stretch using any of these rules. Instead of that, we can use them repeatedly. So, let us look at what is called repeated trapezium rule. So, instead of integrating a function between the limits a to b at a single stretch, we can actually divide this into number of strips. Here, for example, function f x needs to be evaluated between the limits a to b, and this limit or the region a to b is divided into 3 strips, and width of each strip is b minus a divided by k, where k is the number of strips. Here in this case it is 3. In the previous figure whatever we have seen, k is equal to 3, but it can be something else for a different problem. So, for this each strip we need to apply trapezium rule and sum it up, then we are going to get the repeated trapezium rule for this problem or for this integral, and that is going to be as shown in the equation here, and this equation can be rearranged in this manner. So, this is about repeated trapezium rule. So, the previous example which we already considered can be solved using repeated trapezium rule with k is equal to 3, applying this formula. Only thing is we need to know what is h here. H is going to be upper limit minus lower limit divided by k. So, doing calculation, it turns out that k is equal to pi over 12 for this problem, and applying this formula we get approximate value of the integral as given in this equation, and simplification of this results in this value 0.7031, and a comparison of this with the exact solution which is 0.7071 shows that the accuracy is improved. It may be remembered that a single application of trapezium rule gave 0.6704. Now, let us look at repeated Simpson's rule. We need to apply same logic. Instead of integrating at a single stretch a function or integral between the limits a to b, we divide this width a to b into number of strips of width h. So, h value depends on the number of strips and the distance between a to b. So, when we apply this repeated Simpson's rule, integral f x between the limits a to b turns out to be this one, or which can be further simplified. Here I think because of font problem, equal approximation symbol is not coming properly. So, now let us apply Simpson's rule to estimate this integral, taking k is equal to 4. So, width of each strip is going to be upper limit minus lower limit divided by 4, and it turns out that h is equal to pi over 16, and applying repeated Simpson's rule here results in this approximation of the given integral, which can be further simplified as 0.7071, and exact solution is also, it matches very accurately with the exact solution up to the 4 significant digits that are shown there. So, this is about Newton-Cotes rules. So, in summary, Newton-Cotes rule of order of n number of points results in exact solution of integral of order n minus 1, or if we want to integrate a function of order n exactly, we need to use a Newton-Cotes rules having n plus 1 number of points. So, if you want to integrate a function of order 0, that is a constant function, we need to use 1 point, and if you want to integrate a linear function, we need to use 2 point. If we want to integrate a quadratic function, we need to use 3 points. So, now let us look at Gaussian quadrature, also called as Gauss-Legendre rules. We will understand why its Legendre word is there. So, now in Gauss-Legendre rule, basically for 1 point rule, or it is also called midpoint rule, that is n is equal to 1, we are going to evaluate function at a single point which is midpoint, or this is the equation that is shown here is a general equation for Gauss-Legendre rules or Gauss quadrature, that is integral fx between the limits a to b is approximated as function evaluated at certain points multiplied by the corresponding weights. For n for 1 point rule, n is going to be equal to 1. So, function integral minus 1 to 1 fx dx is approximated as some weight times function evaluated at midpoint of minus 1 to 1. What is midpoint of minus 1 to 1? It is 0. So, function is evaluated at 0, and weight here is 2. So, 2 times function evaluated at 0. So, basically whatever may be the order of function, whether it is constant, linear, quadratic, cubic, quartic or fifth order function, basically it is replaced with a constant function as shown in the figure. Fx is replaced with q naught, and in 1 point rule this integral minus 1 to 1 fx dx is evaluated by using the function evaluated at the midpoint of the range over which integration needs to be performed, multiplied by the weight, which turns out to be 2 here for this 1 point rule. So, now let us look at how this 2 is obtained, how 0 is obtained for location, how 2 is obtained for the weight. We will understand it better when we look at 3 point rule. So, now let us look at 2 point rule, that is n is equal to 2. Again function fx or the integral fx minus 1 to 1 dx is approximated as w1 times fx1 function evaluated at x1 plus w2 times function evaluated at x2. So, now let us understand how to get these weights and weights w1, w2 and x1, x2. Just before I made a statement that the procedure will be clear when we take n is equal to 3, but let us look here itself for 2-point rule how to get these weights and locations x1 x2. So there are 4 unknowns to be determined x1 x2 w1 w2. So one can easily guess we require 4 equations to uniquely determine this w1 w2 x1 x2. So what we will do is we will play the same, or we will use the same logic as what we did for getting the weights for Simpson's rule. So let us start with fx is equal to 1. We need to get 4 equations. So let us start with fx is equal to 1, fx is equal to x, fx is equal to x square, fx is equal to x cube, and we get 4 equations. So when we substitute fx is equal to 1, we get this equation, integral 1 dx between the limits minus 1 1 is going to be 2, and substituting fx function evaluated x1 is equal to 1, function evaluated x2 is equal to 1, we get this equation. Similarly, that fx is equal to x, again x is the odd function, we are integrating over a symmetrical domain. So integral turns out to be 0, and fx is equal to x means function evaluated at x1 is going to be x1, function evaluated at x2 is going to be x2. So we get this equation 0 is equal to w1 x1 plus w2 x2, and let fx is equal to x square, again x square is an even function, integrating this over a symmetrical domain results in a non-zero value which is going to be 2 over 3, and function evaluated at x1 is going to be x1 square, function evaluated at x2 is going to be x2 square. So that gives us this equation 2 over 3 is equal to w1 x square plus w2 x square, w1 x1 square plus w2 x2 square, sorry, and fx is equal to x cube, again x cube is an odd function, we are integrating over symmetrical domain. So integral turns out to be 0, fx1 function evaluated at x1 is going to be x1 cube, function evaluated at x2 is going to be x2 cube. So that results in this equation 0 is equal to w1 x1 cube plus w2 x2 cube. So we got the 4 equations that we actually looking for. So we can solve these 4 equations for the 4 unknowns x1, x2, w1, w2, and the solution results in these equations. X1 or x2 is plus or minus x1, w1 is equal to w2 is equal to 1, and x1 square is equal to x2 square is equal to 1/3, and simplification of previous equation results in this, and w1 is equal to 1, w2 is equal to 1. So basically 2-point Gauss-Legendre, according to 2-point Gauss-Legendre rule, we are going to evaluate function at minus 1 over root 3 and 1 over root 3 and multiply with corresponding weights and add them together, that is corresponding weights are 1 here. So it is basically function evaluated at minus 1 over root 3 plus function evaluated at 1 over root 3, and this is what is schematically shown in the figure. The original function fx is replaced with a linear function or function q1, original function is replaced with a function q1, and the function is evaluated at 2 points x1 and x2. So estimate the value of this integral, and the order of integrand here is, the highest order of integrand here is 3, and let us evaluate this integral using 2-point Gauss-Legendre rule. So we need to evaluate function by substituting in the previous equation x is equal to minus 1 over root 3 and x is equal to 1 over root 3, we get this, and it turns out that the approximate solution is same as exact solution. So what we can learn from this is, if we use Gauss-Legendre rule, if we adopt Gauss-Legendre rule, we can integrate a function of order 2n, Gauss-Legendre rule of n points can integrate a function of order 2n minus 1 exactly. So we can integrate a function up to order 2n minus 1 exactly if we adopt n number of points. So 2-point Gauss-Legendre rule integrates cubics exactly, a function, cubic function exactly. And this can also be extended for, this procedure can also be extended for more number of points. So now let us see 3-point Gauss-Legendre rule, that is n is equal to 3. So integral minus 1 to 1 fx dx is approximated as function evaluated at 3 points x1, x2, x3 multiplied with corresponding weights w1, w2, w3 and sum them up. So this is how we can approximate this integral. So we need to determine these weights and locations w1, w2, w3, x1, x2, x3. And what about the accuracy? This formula will be exact for a function up to order 5, because a n point Gauss-Legendre rule is going to be exact in evaluating an integral having integrand of order 2n minus 1. So how to determine these weights and these locations? We need to adopt similar procedure that we already looked at. So we need to get 6 equations to determine these 6 unknowns uniquely, that is fx is equal to 1, fx is equal to x, fx is equal to x square, fx is equal to x cube, fx is equal to x power 4, fx is equal to x power 5. So we impose these conditions and we determine these 6 unknowns, and it turns out that the 6 equations, the solution of 6 equations results in this, that is w1 is equal to w3, x1 is equal to minus x3, x2 is equal to 0. So in the figure the locations of these integration points is shown. That is x1 is equal to minus root 3 over 5, x2 is equal, x3 is equal, x2 is equal to 0, x3 is equal to root 3 over 5. So integral fx between the limit minus 1 to 1 is basically approximated as 5 over 9 times function evaluated at minus root 3 over 5 plus 8 over 9 times function evaluated at 0 plus 5 over 9 times function evaluated at root 3 over 5. So this is a procedure that we can follow even if one desires to find what are the locations and weights for more points in Gauss-Legendre rules. So now basically we have the weights and locations for these Gauss-Legendre rules. For any number of points we can derive, there is no problem, and also all these are well documented in any of the textbooks on finite elements or any numerical methods. So now the formulas or the weights and locations are available for the limits minus 1 to 1. So if limits are something else, we need to discuss what what will be the procedure. So, changing limits of integration. So, if one wants to evaluate this integral a to b fx dx, we need to somehow bring into the form -1 to 1 some integrand. So, the procedure is like this. So, we can use this changing this formula to change the limits of integration, that is limits a to b are changed to -1 to 1 using this formula x is equal to b minus a times t plus b plus a divided by 2, and when we take derivative of this equation on both sides, we are going to get dx is equal to b minus a over 2 times dt. So, this is how integral with limits other than -1 to 1 can be changed. So, now let us estimate, but the rest of the procedure, once we get an into the form -1 to 1 integral -1 to 1, the rest of the procedure similar to what we already discussed. So, now let us estimate the value of integral 1 to 4 x cos x dx. So, first job is to change the limits of integration, and here also it is mentioned that we need to use 3-point Gauss-Legendre rule. So, first job is to change the limits of integration. So, we need to make a substitution, x is equal to 3t plus 5 over 2 and dx needs to be replaced with 3 over 2 dt. So, making these substitutions, we can proceed as we already discussed by taking 3 points. We already know what are the locations and what are the corresponding weights. So, this integral, when we substitute this, when we make this substitution of x in terms of t and dx in terms of dt, this integral, that is integral 1 to 4 x cos x dx becomes, or the x cos x is plotted here as a function of x, and the locations of the integration points are shown in this figure. So, we need to evaluate the function at these points x1 x2, that is t the integration point which is located at minus root 3 over 5, it corresponds to x1 is equal to 1.34, integration point located at x is equal to 0 corresponds to the point x2 is equal to 2.5, integration point located at root 3 over 5 corresponds to the integration point 3.66. So, using the previous change of integrations, change of limits of integrations, we get these integration points. So, we need to evaluate function at these integration points. So, substituting the change of limits into the previous equation of integral, we get this equation, and substitution of weights and sample points, we get this approximation. Actually, there is some problem with font again, brackets are shown as some blocks there, and when this integral is when they simplified, it turns out that this integral value is minus 5.0611, and when we compare this with exact solution turns out to be minus 5.0626, which is very close. Which is very close to the exact solution. So, now we can summarize Gauss-Legendre integration points and corresponding weights in a table like this. Here only up to n is equal to 4 is shown, but as I mentioned, in any of the standard textbook on finite element method or any numerical method, we can find integration points up to more n is equal to up to 10 or more, and also these values of locations and weights are also can also be obtained in any of the commercial softwares like MATLAB. So why it's this word Legendre is actually these locations or functions of this, or it can be shown that these locations, that is excis or roots of this Legendre polynomial, that is why it is called Gauss-Legendre integration rule or Gauss-Legendre rules, or for that matter most of the finite element textbooks refer this as Gauss quadrature in a simple in a very simple form.